Okay, let's dive in. We're looking today at a really structurally rich sequence from the OEIS A000366. Now, the formal definition, it sounds pretty dense. It's the Genocchi numbers of the second kind, divided by 2 to the power of n minus 1.
Right. And you hear that definition, you hear divided by, and you immediately think, okay, fractions, right?
Right.
But that's the first bit of magic here. Despite dividing by this power of 2, the result is always a whole number, a positive integer.
Always an integer.
And that consistency, that's really the first major clue that something interesting is going on.
Yeah, and let's just list the first few numbers so people get a feel for it. It starts 1, 1, 2, 7, 38, 2, 95, 30, 0, 98. They grow pretty fast. And what's really fascinating is this isn't some obscure new thing.
No, not at all. Don Knuth points out this sequence has, well, over a century of history. The earliest known reference seems to be the Delac and Marcel memoir, way back in 1901.
1901. So we're talking classical math here.
Exactly. It's classical, but, modern combinatorialists are still digging into its interpretations.
Okay, so let's start with maybe the most visual one. The one from Ira Gessel, building on Delac's work.
Ah, yes, the Delac configurations. It's a beautiful combinatorial puzzle, really. Imagine a grid, a specific one. 2 n rows and n columns.
Okay, 2n by n.
And within a certain diagonal set of cells on this grid, you're counting subsets of these cells. But there are rules. You need exactly 2 cells from each column and exactly 1 cell from each row.
2 per column, 1 per row. That sounds quite constrained.
It is. Very specific. And the number of ways you can do that number is an, our sequence number. A physical counting problem defines these numbers.
So you can actually, draw this out for small n.
You could, yeah. It gives you a very concrete geometric handle on these numbers.
Right, but then things take a turn, don't they? Evgeny Fagin comes along with a completely different angle, more algebraic.
That's the leap, yes.
Yeah.
And it's a significant one. Fagin connected these same numbers, an, to something seemingly unrelated, counting specific sequences of nested subsets.
Nested subsets of, the numbers 1 to n.
Precisely. Sequences of subsets of 1 with certain properties. And the connection goes even deeper into algebraic geometry and topology.
Okay, wait. Topology. You mentioned Euler characteristics and flag varieties. That sounds advanced.
It is. It involves the Euler characteristics of what are called degenerate flag varieties of type A.
Right. So for maybe listeners who aren't dealing with flag varieties daily, what does Euler characteristic signify here? What's it measuring?
Think of it simply as a kind of sophisticated counting tool. It's a number assigned to a topological space that tells you something fundamental about its structure, its complexity.
Okay, a structural invariant.
Exactly. And the mind-blowing part is that Fagin showed this abstract topological invariant, this Euler characteristic, is the same number you get from just counting those simple cell configurations in Delac's grid.
Wow. So the grid counting somehow knows about this deep topological structure.
That's the remarkable insight. The combinatorial constraint mirrors the algebraic topology.
That's stunning. Okay, so we have geometry, we have algebra and topology, but there's number theory hiding in here too, right? These aren't just random integers.
Oh, absolutely not. They are highly structured. Barsky found some really strong congruence patterns. For instance, if n is even and bigger than 1, an is always 3 modulo 4. Always.
Always 3 mod 4 for even n. What about odd n?
For odd n, again bigger than 1, an is always 2 modulo 4. So 2, 3, 2, 3 modulo 4.
Okay, that's already quite rigid.
And there's more. Kerr has discovered another pattern. If you look modulo 36, for n greater than 2, the values of an just alternate between 2 and 7.
2 and 7 modulo 36. Let's check. A3 is 2, A4 is 7. Wait, no, A4 is 38. 38 mod 36 is 2, at 5 is 295, 36. 295 is 836 plus 7. So yeah, 7. It works.
It holds. It's this incredible underlying arithmetic pattern. You look at the start, 1, 1, 2, 7, 3, 8. You wouldn't guess such strict rules govern them.
No way. And this structure, it even ties back to really fundamental objects in math. You mentioned Bernoulli numbers.
Yes, that seals the deal, in a way. There's a formula that explicitly connects an to the classical Bernoulli numbers, bk. It involves a sum with binomial coefficients, and terms like 1, 2, n plus k plus 1 times bn plus k plus 1. It shows these numbers are deeply rooted in classical analysis.
So pulling it all together, A000366 isn't just one thing, it's like a bridge.
Exactly. It connects Delac's very visual cell counting
to Fagin's abstract algebraic subset sequences and flag varieties.
And its growth is governed by these strict number theoretic congruences, and it's ultimately built from classical Bernoulli numbers. It's a nexus point.
A mathematical Rosetta Stone, almost.
That's a great way to put it, translating between seemingly disparate fields.
Okay, so for a final thought, something for our listeners to chew on, where else can they see the complexity?
Well, if you really want to see the intricate machinery behind these numbers, look up the generating function for A000366. It can be expressed as this just dramatic continued fraction. Not a simple one, it involves nested products.
Nested products inside a continued fraction.
Yes, exploring that structure.
Yeah.
It really unveils a whole other layer of complexity and connection. It hints at why these numbers behave the way they do. It's quite something.
Definitely something to explore further. Fascinating stuff.